Okay, sorry for the delay. Okay, hope my voice is audible to all, right? Or I was in mute. Yeah, I was.
Yes, sir.
Yeah, fine. Okay. So now we will discuss about momentum optimizer, how it will work. So before going to momentum optimizer, so generally in machine learning, your cost function or objective function is like a convex shape, right? Like a bowl shape, right? So we are assuming initial point random. We are choosing an initial point, and this point will be slowly updated and comes towards its global point or optimal point, right? So forget about this one. So I am assuming it is a bowl. It is a bowl, and just I drop a ball here. Right? So if I drop a ball here, then it will move along the curvature of the bowl, right? It moves in the downward direction along the curvature of the bowl, right? Fine. So do you think that will come down and come and saturate here? No, because of its momentum, its energy, it will fall down. It will not stable here, but it may move up to here, and again it come back, and it will move up to here, and again come back, and it will move up to here, and come back, it will move up to here, and finally comes to the saturation position. So that means because of its momentum, when it is falling from high slope, because of its momentum, then what happened? The ball will be oscillating around its saturation point or final point. Right? I think you understood, right, what I am telling? Fine. Okay, I am explaining again. Let us assume a bowl which replicates the convex function in our machine learning or in our optimization problem. In the bowl, I took a ball here like an initial point in our optimization algorithm. If I fall down this ball from here, as the point starts falling from here and slowly reaches to the optimal point, similarly, just a ball I kept here and leave from here, then it will follow the curvature of the bowl and come down. It will not stop at the bottom point or minimum point or optimum point directly. Instead of stop here, what it will do? It will move up to some way like this, and later it is come falling down and moves up to here and here and here, and finally it reaches this point. So there the oscillations will be happening. Right? So in the similar fashion, in the gradient optimization approach, the point will be moving slowly, and it is following the curvature of the function and coming down. It may not saturate, and it may not stop here. It may jump somewhere point here, and later here, and finally comes here. That type of operation will be happened in case of the large eta value. Suppose if you put a large eta value for the fast convergence, this oscillation may be happening, right? This oscillation may be happening because of its momentum nature. Then what we have to do if you want to reduce these oscillations? What you have to do? So what you have to do if you want to reduce the oscillation means, if you drop a ball from this point, then you try to do something so that its momentum or its weight will be increased gradually as it reaches to the bottom point. Then what happens? If its weight increases gradually while reaching its bottom point, then the number of oscillations will be decreased, right? If it is a lightweight ball, that may be more oscillations. Once ball weight is more, then more force will be towards that is called gravitational force that come down, so that it will become stable here. That means you can add some momentum, some weight onto the ball, then definitely the maximum oscillations will be reduced, and it will comes into the stable position here. So that is that criteria, that physics criteria we are taken care in the momentum optimization. So in the momentum optimization, how we are updating our model parameter, try to recollect, we are updating the model parameter x equal to x minus eta into dou f by dou x. It's called a gradient, and this is the learning rate, this is the previous x value. So this is the procedure actually we are following in case of SGD or BGD or MBGD, right? But what it is suggesting it, if we follow this procedure, if you choose large eta value for faster convergence, it may took the oscillations, it may not converge at the saturation point or optimal point. It will lead the overshoot or oscillations. So to avoid that one, what I want to do is, so this is the x and this is the minus eta into dou f by dou x. Now I want to add some momentum. I want to add some momentum Vt minus 1 to this fraction. This is the minus term, right? So this is the plus term. So I am adding some momentum. Some momentum means we are trying to add some friction type of thing. We are trying to add some opposite force so that it will not move in the opposite direction. It will not go to the oscillations. It will not move in this direction. We are trying to add some friction, some force, some weight, so that it may not move in this direction and slowly comes down. It may saturate at this optimal point. So this is like a, see, I will write again here. This is the x plus gamma, that is called momentum coefficient, Vt minus 1, that is the velocity, like a momentum term, velocity. This is a here it is a positive symbol, you have to observe positive symbol, minus eta into dou f by dou x, it is a negative symbol. See, both are negative, then that will be added again. So one is positive, another is negative, then what happened? So that means we are adding some friction. We are adding some friction. For example, I am giving one more example to you. Let us assume we are riding a bicycle on a road which is like a completely U shape, or in between the hills. Let us assume in between the hill, your road will be completely U shape, that is exists in the hills, in between the hills, U shape. Now you are riding the bicycle. When you start your point from here, then it will come down fastly. It won't stop, it will go here and again come back and come back. It will be moving like this, your cycle will be moving like this. Fine. Instead, suppose if your cycle is moving in this direction, if I am applying some force in the form of opposite wind, I am applying some opposite I force wind against you, then your speed will be comes down when it reaches to this point. Speed will be comes down when it reaches to this point, right? The same thing I am using here. This is the one parameter, minus sign. I am adding the another parameter with the positive sign, so that to reduce that momentum in the ball or momentum in the updation of your point, right? So I will explain some numerical calculation and you can easily understand. So what I want to, in what direction I want to update the point is x equal to x plus initial value, and now this portion is like a delta x, that is the gamma momentum coefficient Vt minus 1 previous velocity minus eta dou f by dou x. It's a gradient. So it is similar to the SGD. Only new term coming here is the momentum term. So we are adding some momentum onto the ball or onto the point so that it not moves high oscillations. Second thing what we are expecting from here is, friends, I am asking one question. Here T means iteration number. So let us assume I am in the first iteration. Right? Then what is the updation? X plus gamma into V0 minus eta into dou f by dou x. So that means you have to initialize the velocity. You have to initialize some velocity. So while initializing, we are initializing the velocity equal to 0. You are initializing the velocity equal to 0. Right? And this complete term is called as a velocity term. This complete term is called as a velocity term. So Vt equal to gamma into Vt minus 1 minus sigma into dou f by dou x. Right? Hello?
Sir, Kiran sir వస్తున్నారంట యాడ్ చేయమన్నారు సార్.
Yeah, okay. Thank you. So this is the velocity term, right? So I want to calculate the velocity at the first iteration. I want to calculate the velocity at the first iteration. So first of all, you have to calculate the velocity at the first iteration. V1 equal to gamma into V0 minus eta into dou f by dou x. V0 means you have to initialize in the first iteration, that's equal to 0. Then your V1 equal to minus eta into dou f by dou x. So this is your V1, right? Your V1 is depending upon the gradient in that iteration, right? Now you have to add this V1 to your parameter x equal to x plus V1, like that you are updating. Same thing I am writing here. V1 is nothing but gamma into Vt minus 1 minus eta into dou f by dou x, right? So why I am telling this one is, see, now in the second iteration, when we are in the second iteration, then what is the updation? What is the updation? X equal to x plus V2, that's equal to where V2 equal to what is the V2? Here V2 equal to, don't worry, I will explain when we are going to numerical calculation, then we can easily understand. Right. What is the
I can't see your screen, sir.
Ma'am? So V2 equal to gamma into V t minus 1. T minus 1 means 2
now
minus 1.
I can see now.
Yeah.
Where you're writing?
Hello, madam.
Okay, sir.
Gamma into V1 minus
No problem.
eta into dou f by dou x at the current second iteration. Dou f by dou x at the second iteration. Now what is the V1? It's V1 coming from here, right? Your V1 is depending upon gradient at the first iteration. Your V1 is depending upon gradient at the first iteration. Your V2 is depending upon gradient at the second iteration. V2 is depending upon gradient at the second iteration. Your V1 depending upon the gradient at the first iteration, whereas your V2 term is depending upon the gradient at the second iteration, right? So what happened here? See, suppose if your gradient in the second iteration and gradient in the first iteration, that means this portion, both are in the same direction, both are the negative, then your step length will be large. If both are positive, then both are step length will be large. But if one is positive, one is negative, then your step length will be reduces. Right? That means what this momentum taker is, suppose if you are moving from initial point and slowly, moving towards the global minimum, if your slope is same in the direction, then your step length will be large. If your gradient is varies, here your gradient is negative and here is gradient is positive. If that case is happening, one gradient is positive, one gradient is negative, like this, then what happened? The step length will be reduces, then it will not move from this point to this point, it will move from some slow step length. Hope you understand, right? So I will explain again, because we have to understand this concept. Only for numerical calculation this thing is not required, but why we are taking all the things I have to explain. Fine. So how momentum will update your point or decision variable x equal to x plus Vt, okay, whereas Vt equal to gamma into Vt minus 1, that is the initial velocity, minus eta into dou f by dou x, right? So now if you want to calculate the gradient in the velocity in the second iteration, if you want to calculate the velocity in the second iteration, then the velocity in the second iteration is depending upon gamma into V1 minus eta into dou f by dou x in the second iteration, at iteration t equal to 2 in the second iteration. So this is the gradient in the second iteration, and this is the velocity in the first iteration. Now what is the velocity in the first iteration? We will discuss now. So velocity in the first iteration equal to gamma into, velocity in the first iteration equal to gamma into V0 minus eta into dou f by dou x in the first iteration at time t equal to 1. That means if you want to calculate the velocity of a position, velocity of your point while moving from initial point to the global point, towards the global point, its velocity is depending upon two factors. One is v1, nothing but gradient in the first iteration, that means previous iteration, and also gradient in the current iteration. Understand? So your velocity, current iteration velocity in the current iteration is depending upon the two factors. One is gradient, one is v1 is nothing but the gradient in the first iteration plus, so this is the gradient in the second iteration. So it will depending upon both. Suppose the both are negative, if the both are negative, then your v2 will be negative value some large, negative large. If both are positive, then it is a positive large. That means what it means, if both slopes are negative, then you want the high step length. If both slopes are positive, then only you can take the high step length. But if one is positive and another is negative, if one is positive and another is negative, or it is a negative, it is a positive, then what happened? The addition will be decreases. When you do the addition between one positive and negative number, the net amount will be decreases, right? That means in that case, your step length will be decreases. So what happened because of that one? If you take care of like this, what impact that will have on the optimizer while searching the optimum solution. So we will discuss about this one. Fine. So this is your convex objective function, and this is your initial point. At iteration 1, this is your initial point, right? And in the second iteration, you are calculating the velocity here. So because both are in the positive slope, so you will get the large, both are in the positive slope. That means at this point you have the positive slope, at this point also you have the positive slope, you will get the large step length. And at this point also positive slope, you get the large step length. At this point also you have the positive slope, you are getting the large step length. And whereas the first iteration, second iteration, third iteration, fourth iteration. Where fifth iteration, if you get the point here, then what happened? This is in the positive slope and this is in the negative slope. So one is positive, another is negative. When do the velocity calculation, then the velocity vector value reduces. Then your step length will be not from here to here, it will be come down somewhere here. That means it will try to reduce the oscillations at bottom of your convex function. Try to reduce the oscillations at bottom of the convex functions. So because of that reason, this type of mathematical modeling is take care while doing the momentum expression. Right? So we will discuss now how the momentum will work for simple linear regression model. So try to remember one thing, your decision variable will be updated in this fashion: x equal to x plus vt, where vt equal to gamma, that is called momentum coefficient, vt minus 1 minus eta into gradient of the function with respect to the decision variable. You have to take care of these two equations. I hope you understand, right, why we are taking like this. One is the momentum factor, so that if you add some momentum on the ball or on the point, the acceleration at the bottom will be reduces. And the second thing is, so if the current iteration point, next iteration point are in the same slope, then your step length will be high value. If in the opposite slope, then your step length will be reduces, so that the point will be comes at the optimal point, at the bottom peak point. Right? So what I am to tell you is, so this is depending upon the gradient of the previous iteration. This is depending upon the gradient of the current iteration. If both gradients are positive, you expect a more step length. If both are negative, you can expect a more step length. but one is positive, one other is negative. That means you are reaching near to the bottom peak of your convex point. Then don't go for the large step length. If you go for the large step length, then it will move from the positive to the pure negative slope. It may skip the bottom point, right? So that take care by this momentum equation. Fine. Now we will discuss how we can a simple linear regression model will update the model parameters. Sorry, how momentum optimizer will update the model parameters of simple linear regression model. Right? Let us assume as we are working on the simple linear regression model, take one input x corresponding output y. Right? So there is some samples. There are some samples. So it's called xia. I represent the sample number, a represent the actual value, and yia. So this is the data. Now, almost similar to the previous algorithms, in the first step, you have to initialize all the parameters of your algorithm. First, you have to read your data set. And what else we have to initialize? So based on the last three algorithms knowledge, can you tell me what we have to initialize? So in the first step, we are going to initialize the parameters, right? So what we are going to initialize in the first step? Anyone, please? So similar to the remaining all algorithms.
Learning rate.
Madam? So what you have to initialize here?
The learning rate, sir.
Yes, ma'am. Thank you. So one is the learning rate. So let us assume it is 0.1 something or whatever it may be. And what next, madam? So we have to initialize model parameters. Let us assume m equal to 1. Yes, madam.
Epochs.
C equal to -1. And epochs, number of iterations you have to initialize, that's equal to, let us assume whatever it may be, 100. And what else I have to initialize? Anyone can tell? So up to here it's fine in case of stochastic gradient descent optimization or batch gradient descent optimization. Inkoti nana?
Number of samples. Velocity
okay.
E not equal to 0.
Number of samples. What we have to take equal to 0?
Velocity.
Yes,
Initial
perfect,
velocity.
perfect, right. Initial velocity. So initial velocity with respect to the each model parameter we have to consider. See, for every decision variable there is a one velocity vector. Decision variable is nothing but the model parameter in our machine learning case. So for every model parameter you have to take the one velocity vector. So your initial velocity vector Vm equal to Vc equal to 0. Vm equal to Vc equal to 0. So this is the velocity for the model parameter M, and this is the velocity for the model parameter C. Right? Now step 2. So in step 2 what you have to do? So you have to set eta equal to 1. Step 2 we have to take the iteration equal to 1. In step 3 you have to take sample equal to 1. So in this momentum optimization, I want to update the model parameters step by step. So yesterday I told na, so you can take different type of batch sizes. So here also in momentum also you can take different type of batch sizes. You can take a sample by sample, or you can take a different batches, or you can take all samples at a time as a batch. You can apply anything for this momentum also. Okay, so you can implement momentum optimizer with single sample, or you can with complete batch, or you can do it with mini batches also. So for the demonstration purpose I am taking the sample by sample. That means I want to take the first sample and update the parameters using the momentum optimizer. Okay, now take the sample equal to 1. Now step 4. So what you have to do, ఎవరైనా చెప్పగలరమ్మా? పర్లేదు, మీరు జస్ట్ ఆలోచించి చెప్పండి. రైట్ ఆర్ రాంగ్ ఇస్ నాట్ an issue. So what maybe in step 4 we have to do? What we have to do in the step 4? Okay.
velocity.
Velocity calculation అంతేనా? We need to calculate velocity.
Yes, sir.
Yeah. So suppose if you want to calculate the velocity in the first iteration, then v1 equal to gamma into v0 minus eta into this term. What is this term? It's a gradient, right? Suppose if you want to calculate the velocity at iteration t equal to 1, iteration equal to 1, then your velocity equal to gamma into velocity in the previous iteration, that's equal to initial velocity. Okay, that is a 0, minus eta into dou f by dou x means it's a gradient, means so we need gradient, right? If you want to calculate the velocity, you need the gradient, right? So you have to calculate the gradient first, later we will calculate the velocity. Fine. So first you have to calculate the gradient. So calculate the gradient with respect to the your model parameter m. So anyone can tell what may be the expression for the gradient in this case? What will be the expression for the gradient in this case?
Without summation, only one.
Perfect. Thank you.
Only
That
one
depends
sample.
upon the batch size, sir.
Yes, definitely. So in the demonstration, I am taking the sample by sample. So I'm taking the one sample and I want to update the model parameter, right? So as I'm taking the sample by sample, not as a batch, so you can use the without segmenter. That's equal to minus yia minus m into xia minus c into xia. Similar to the your stochastic gradient approach. So gc equal to minus yia minus m into xia minus c. So this will not come into picture here. Fine. So we are calculating the gradient of your cost function or loss function or error function, that is of mean square error, with respect to the model parameters m and c. So after calculating the gradient, what you have to do in step 5? After calculating the gradient in step 5, you have to find the velocity. You have to find the velocity with respect to the each model parameter. So I want to take it as a 0 initial. So we can call it as a forget about this. So your velocity Vm equal to gamma into Vm. This Vm means previous value minus eta into dou, that is dou e by dou m means, so we can call it as a gradient. Right? Similarly, Vc equal to gamma into Vc minus eta into Gc. So I forget one thing to initialize here. What is that value? That is momentum coefficient gamma.
M and C.
MNC already there. Okay. So I forget to initialize the gamma momentum coefficient. So generally we are preferring the momentum coefficient as high value, that is a 0.9. Generally it is varying from 0.5 to 0.9. In this case I am considering the momentum coefficient as 0.9. Fine. So you have to update the velocity for the model parameter m, velocity for the model parameter c equal to gamma 0.9. Vm, that is the previous velocity. What is the previous velocity? 0. Minus eta, it is coming from 0.1 here. Gm, it is coming from here. Same thing for the velocity for the Vc also. Vc equal to gamma into this Vc will be coming from here and Gc will be coming from here. Like that we are calculating the velocity. So after calculating the velocity, we have to update our model parameters. So in the next step, we are updating the model parameters. So those are step 6. I am updating the model parameter m. So m equal to m plus Vt or Vm, current iteration, and c equal to c plus Vc, that is the velocity in the current iteration. This Vm and this VC will be coming from in the step 5, VM and VC. So we are updating our model parameter. So why I am taking this momentum term, I will explain, already explained in the previous board. Okay, that is step 6. So now in the step 7, now what you have to do, you have to update your sample. So sample equal to sample plus 1, that means you are updating sample number, right? Now the sample number equal to 2. Now in step 8, what you have to do, you have to check for your sample count. If the sample count less than or equal to number of samples ns, then we have to go to which step? If the sample count less than the number of samples, that means your current sample is less than the total number of samples available in the training data set, then we have to go to which step?
Step
Step
4, sir.
Yeah, thank you. It is a, we have to go to the step 4, where we are calculating the gradient at the current, for the current sample. Gradient with respect to the model parameter M, model parameter C for the current iteration. Suppose else, that means you are reaching the maximum number of samples available in the data set, then you are go to next step. So next step means that is the step 9. In step 9, what you have to do is you have to update the iteration count. So iter equal to iter plus 1. You have to update the iteration count, that is the iter equal to iter plus 1. Now go to next step, that is step 10. In step 10, you have to check for the iteration whether it reaches the maximum number of epochs or not. Whether you are reaching the maximum number of epochs or not. If you are reaching the maximum number of epochs, then you have to go, suppose if you are not reaching the maximum number of epochs, if it is true, you are not reaching the maximum number of epochs, then you are going to which step?
Step 3, sir.
Step 3. Again we have to start from the first sample. Else, go to next step. So else means you are reaching the maximum number of iterations. Then go to next step, that is called step 11, where you have to take the latest M and C values, model parameters. You have to take the latest model parameters of the given machine learning model. We are considering the simple linear regression model, so that I am considering the M and C. I am considering the M and C. So later you have to calculate the error matrices on both training data set and also on the testing data set. So optimizer to optimizer, only change is how you are updating the model parameters. That's it. How you are updating the model parameters, right? In case of the stochastic gradient, that is the m equal to m minus eta into dou f by, some dou L by dou m, or gradient with respect to the m, right? So but here in case of the momentum, that will be changes. We are considering the momentum factor also. So what is the benefit of this one is, you can choose some large eta value. Even though you choose some large eta value, because of the momentum factor, it may not go to the oscillations, it will comes to convergence fast when compared to the simple gradient descent optimization techniques. So it will avoid the oscillations because it updates the position of a parameter in such a way that if the parameter in the current iteration and the previous iteration are in the same line, then it will take the large step. That may be in the negative slope or in the positive slope. But if the current iteration slope and the next iteration, the current iteration slope and the previous iteration slope are in the, that means what I am saying, are in the opposite side, one is in the negative side, one is in the positive side, then it will reduce the step length, because one is positive, another is negative. So one is positive and another is negative, so it will lead the less value of velocity, which will lead the less updation in the model parameters M and C, right? Fine. So this is the algorithm for momentum optimizer for a simple linear regression model. Now we will do some numerical calculation by taking the same example what we discussed for the stochastic and batch and a mini batch gradient takes. So it is a 0.2, let us assume it is a 3.4, and it is a 0.4, and it is a maybe 3.8, let us, 2 samples, okay. So I want to do the numerical calculations and how it will help you to know how the momentum optimizer will update the simple linear regression model weights or parameters, model parameters. So in step 1, so you have to initialize the read the data set xia and yia, set the set the learning rate 0.1, whatever it may be, number of epochs, maximum number of iterations. As we are doing the hand calculations, I am taking the only one, and initialize your model parameters as m equal to 1 and c equal to -1. For this hand calculations, I am taking the 1 and -1, but you have to generate randomly, and you have to initialize Vm equal to Vc equal to 0, and also you have to initialize momentum coefficient equal to 0.9. Initialize momentum coefficient equal to 0.9. Fine. So we initialize, so, and the number of samples, that the number of samples equal to 2. So we are initialize all the parameters, right? So step 2, go to step 2. In step 2, what you have to do, set iteration count equal to 1. In step 3, what you have to do, set sample equal to 1. Step 3, you have to set the sample equal to 1. Now step 4, what you have to do? Step 4, what you have to do? We have to calculate the gradient, right? We have to calculate the gradient gm and gc. So gm equal to ఎంత వస్తుందమ్మా, మైనస్ వాల్యూస్ చెప్పగలరా ఎవరైనా, YIA, because we are in the sample 1. Sample 1 means this one. So that's equal to minus 3.4 minus m, that's the 1 XIA 0.2 minus c, that is the plus 1 into 0.2, right? So that's value equal to ఎంత వస్తుందమ్మా, I think 3.1, 4.4, 4.2, that is a 0.84 with negative sign. Why negative sign? That's coming from here. Similarly, GC equal to minus 3.4 in minus 1 into 0.2 plus 1, it will not come. So that value equal to 4.2 with negative sign. So you have to calculate the, in the fourth step, you have to calculate the gradients of error function, of mean square error function or cost function or loss function with respect to the model parameter. Next, in step 5, you have to find the velocity. In step 5, you have to find the velocity. So Vm equal to gamma, gamma means it's the 0.9 into Vm. What is the Vm here? Velocity for the model parameter m. Vm equal to 0. Perfect. Minus eta 0.1 into gradient, that is a minus 0.84. Hope. So it will be 0.084. It's a 0, right? So minus into minus plus 0.1 into 0.84, that is 0.084. Similarly, Vc equal to gamma 0.9, initial Vc, that is a 0, minus eta 0.1 into Gc, that is a minus 4.2. So that's equal to 0.42. That's equal to 0.42, right? Now, next step 6. In step 6, what we have to do? In step 6, we need to update our model parameters. That is the m equal to m plus Vm. That's equal to, what is the m value? That is the 1, initial value of m, 1, plus Vm equal to 0.084. 0.084. That's equal to 1.084. Similarly, c equal to c plus Vc. That's equal to, what is the value of c? That is the minus 1 plus Vc value equal to 0.42. Vc value equal to 0.42. Then it will be minus 0.58. Now I am updating my m and c values. I am updating my m and c values. So m value equal to 1.084 and c value equal to minus 0.58. So what, now go to the step 7. In step 7, what you have to do? You have to update your sample number. So sample equal to sample plus 1. That's equal to 1 plus 1. That's equal to 2. Now go to step 8. Go to step 8. In step 8, what we are doing? You have to compare the your current sample with the number of samples. Your current sample is 2 and number of samples also 1 and 2. So it condition is satisfied, right? If condition is satisfied, what I said, you have to go to step number. If this condition is true, you are going to step number
4.
We have to go to which step?
4, sir.
4. We have to go to step 4. Now
Four,
we have
sir,
to do
step
the
4.
gradient with respect to M, gradient with respect to C for the second sample. For the second sample, right? So you have to remember M and C values 1.084 minus 0.58, right? Now we are working on the second step 4 again for the second sample, right? So what is the GM value now? So GM equal to minus YIA, second sample YIA, that's the 3.8 minus what is the M value? 1.084, X value,
1.
right? And it is a minus into minus plus, I think it is a 0.58 updated C value, so into 0.4 into 0.4. So you have to calculate the GM value, you have to calculate the GM value. Similarly, you have to calculate the GC, that's equal to minus 3.8 minus 1.084 into 0.4 plus 0.58. So that is the next one, right? So we are getting the GM and GC values. So once we are getting the GM and GC values, next go to step 5 where we are updating the velocity. So velocity Vm equal to gamma into Vm, sorry, I will rough it. So Vm equal to, tell me, gamma, that is a 0.9 into 0 minus eta 0.1 into Gm. This Gm value coming from here. Is it right? Is it okay now?
VM value is,
Yes. So
sir, VM value is
not this
updated.
one. It is not 0, right? So we have to take the VM value in the previous timestamp. So what is the VM value in the previous timestamp? You have taken from here. So VM value in the previous timestamp 0.084 and this value 0.42. Okay. So 0.084 and 0.42. That is the VM values we have to take, not 0. So profit. So it will be 0.084, so 0.084. So you have to calculate the VM value. So GM is coming from here and all values are known, you can calculate the VM. Similarly, you have to calculate the VC, that's equal to 0.9 into, you can 0.42 na? 4.2.
Yes, sir, 0.4.
Yeah, 0.4.
0.4.
Yeah, 0.42 minus 0.1 into GC. This GC value coming from here. So you can easily calculate the VM value and also you can easily calculate the VC value. Once you have calculated the VM and VC value, go to step 6 where you have to update them M values. M equal to M plus VM. So M value equal to 1.084 plus VM. This VM value coming from here. And similarly update the C, model parameter C, that C equal to C plus VC. So the C value equal to, I think it is the minus 0.58 plus VC, this VC value coming from here. VC value coming from here. So like that you have to update the model parameter M and C. You have to update the model parameter M and C. Right? Now go to step 7. So now update your sample count. So sample equal to sample plus 1, that's equal to, we are in the current sample is 2. So 2 plus 1, that's equal to 3. Now go to step 8. Update, check number of samples. Number of samples are less than or equal to NS or not. So now sample count is 3. But your number of samples are 2. So it's a false case. It is a false case. Then we have to go to step 9. Step 9. In step 9 what we are doing? We are updating the iteration. So iter equal to iteration plus 1, that's equal to 1 plus 1, that's equal to 2. Now in the step 10, so we have to check whether maximum iterations reached or not. If iteration less than or equal to epochs or not. Your current iteration is 2, right? And number of epochs what you initialize, there is a 1. So it is a false now. It is a false. So then we have to go to the step 11. So in step 11, you have to read the latest M and C values. That M and C values are these two. The latest M and C values, you have to read M and C values, and you have to calculate the error matrices on both training data set and also on the testing data set. Right? So this is the procedure we are doing for updating the any type of model, any type of machine learning model. This is the procedure is same, but only thing changes is the number of parameters what we have used. The number of parameters what we have used. Right? So suppose I am asking you, I want to forecast the load at a particular hour of the day based on the load at the same hour but for the last 3 days. What I want to mention you is, suppose if you want to predict the load at 9 o'clock today PM, 9 PM today. If you want to forecast the load at 9 PM today, then your inputs are yesterday 9 PM load, day before yesterday 9 PM load, and before that 9 PM load. Suppose if that is the approach for your load forecasting problem, can you use simple linear regression model? Can you use simple linear? No. Thank you. So you can't apply simple linear regression model because simple linear regression model will be applicable only for the one input, one output. So then we are going for the multilinear regression model. We can do with ANN also, but I am not discussing about the ANN. So we can go with the multiple linear regression model. Okay, multiple linear regression model. Now my question is, if I am going to use if I am going to use momentum optimizer to update the parameters of a multilinear regression model for the load forecasting problem, then how many velocity variables will be available in the learning algorithm? How many velocity variables will be available in the learning algorithm?
4 variables.
Yeah, it is a 4 variables because 3 for the 3 input features, 1 is the bias parameter or C, because your model will be like y equal to m1 x1 plus m2 x2 plus m3 x3 plus c. So 3 velocity vectors for the 3 coefficients for 3 features, vm1, vm2, vm3, and 1 is for the bias, that is vc. So there are 4 velocity points. So you can use a similar step. You can do the similar step. Only thing is your computation will be increased because instead of 2 velocity updations, I have to take care of 4 velocity updations. Instead of 2 gradient calculations, I have to take the 4 gradient calculations. Instead of taking the 2 updates, I have to take the 4 updates. So in step 4, step 5, step 6, the number of computations will be increased. It will be doubled. Yes, it will be doubled. Right? So the procedure will be same. You can call it as a GM1, GM2, GM3, GC, VM1, VM2, VM3, VC, M1, M2, M3, C. Okay, 4 equations will become in the each 4 equations will becomes in the each step. So you can use the same procedure, same algorithm. Only the number of computations will be increased because of the model will become a complex model. Right? So I hope you understand how momentum optimizer will update the model parameters, simple integration model parameters. Right? It's fine, right? So next we are going to discuss about Nastro accelerated gradient. See, as I said in the very first class, all the machine learning algorithms, conventional machine learning algorithms are developed based on the gradient descent optimization only. So from one optimizer to another optimizer, there is only small modification will be exist. That also exists at the time of the model updation. That also exists at the time of the model updation. How model will be updated, how step length will be calculated. That may be changes. That will be changes from the optimizer to optimizer. Rest of the steps will be same. Fine. Now we are going to discuss about NAG, that is called Nastro accelerated gradient. NESTEROV, Nastro accelerated gradient descent optimization algorithm. NAG, NAG, Nastro accelerated gradient descent optimization algorithm. Now we are going to discuss about this one. So what is the main difference? There is small extension for the momentum optimizer. It is the extension for the momentum optimizer. So what is the difference from the momentum optimizer to NAG optimizer is, if you try to recollect momentum optimizer, in momentum optimizer, your step length of your decision variable is depending upon gradient at current iteration and also gradient at previous iteration. Are you agree with that one? Right? అంతే కదా మనం చేసిందమ్మా. So in momentum optimizer, step length means how much length that point will be updated. That is called step length. That is depending upon the gradient in the current iteration and also gradient in the previous iteration. But whereas the Nastro suggested that how I can tell you, so here what we are doing is, your point or your decision variable or your model parameter will be updated based on gradient at the not at the current gradient, but it is based on the next level gradient. So we have to estimate the next point gradient, and based on that one we are updating our model parameter. So it's like a, see, you are riding a bicycle, okay, you are riding a bicycle, and you are riding a bicycle on the road which is like a slightly a slant. I will draw here. So you are riding a bicycle, so that will be like a slant, like this. Okay, you are riding a bicycle here. Okay, so when you are riding the bicycle, so as because of the slant you are moving with that velocity based on the your slope at that point, that is moving like that, based on the your point. What he suggests is, generally manamu, suppose if you are seeing some hurdle here, in front, we are not reaching to this point, we are here only, but I am seeing a hurdle in front of me. So if I see some hurdle, I can change my velocity, right? Based on that one. So something is in front of me, I have to slow down. There is a speed breaker, so I have to slow down. So updating my velocity based on my next position, not at the current position. So such that thing he is considered in case of the natural accelerated gradient optimization, right? ఇంకా పర్టికులర్ చెప్పాలనుకుంటే మనము గాస్ సీడెల్ మెథడ్, వాట్ ఇస్ ద డిఫరెన్స్ బిట్వీన్ గాస్ మెథడ్ అండ్ గాస్ సీడెల్ మెథడ్? In Gauss Seidel method, suppose you have V1 with velocity at the first bus, V2 at the velocity at the second bus, V3 at the velocity at the third bus, right? So when you are calculating the velocity at the second bus, you have to consider the velocity of the first bus also. But while calculating the velocity of the first bus, you are taking the updated velocity, not at the previous velocity. Sorry, previous voltage, right? మీకు గుర్తుందమ్మా మన గాస్ సీడెల్ మెథడ్లో. సో వీ హ్యావ్ టు టేక్ ద voltage at a particular bus, updated voltage, not at the previous voltage. So similarly here we are taking the next level point instead of the only current point we are considered, right? I hope you understand, right? So that is only the difference when compared to the momentum and natural accelerated gradient. In momentum, your step length is depending upon the current gradient and the previous gradient, but whereas in the natural accelerated gradient optimizer, your step length will be depending upon previous gradient and also next gradient, not at the current gradient. But see, we have a problem, right? My question is, suppose this is the previous timestamp, this is the current timestamp, and this is the next timestamp. Okay, now I am in the current iteration. What I am telling is, I want to update the velocity based on gradient at the previous iteration and also gradient at the next iteration. gradient at the next iteration, next point, at the gradient at the next point, right? But see, if you want to get the next point, you have to calculate the gradient here, right? మనం ఇక్కడికి వెళ్ళాలి అనుకుంటే ఈ వెలాసిటీ క్యాలిక్యులేట్ చేయాలి. ఈ వెలాసిటీ క్యాలిక్యులేట్ చేయాలంటే యూ హ్యావ్ టు క్యాలిక్యులేట్ ద గ్రేడియంట్ ఇన్ ద నెక్స్ట్ ఇటరేషన్ కదా. సో నెక్స్ట్ ఇటరేషన్లో గ్రేడియంట్ మీకు కావాలి అనుకుంటే నెక్స్ట్ ఇటరేషన్లో ఉన్న పాయింట్ మనకు కావాలి కదా. మళ్ళీ ఈ పాయింట్ కావాలంటే మనకు వెలాసిటీ కావాలి. ఎందుకంటే మీరు ట్రై టు రీకలెక్ట్. సో యువర్ వీటీ ఈజ్ ఈక్వల్ టు అంటే నెక్స్ట్ లెవెల్కు ఎంత వస్తుంది, వీటీ ఈక్వల్ టు గామా ఇంటూ వీటీ మైనస్ 1 gamma into Vt minus 1 minus eta into dou g by or dou g by dou m, whatever it may be. So this is the gradient at this point. నాకు ఇక్కడ పాయింట్ కావాలంటే ఇక్కడ గ్రేడియంట్ క్యాలిక్యులేట్ చేయాలి కదా, బట్ ఇక్కడ నాకు గ్రేడియంట్ తెలియదు కదమ్మా. సో దెన్ వాట్ ఈస్ ద అప్రాక్సిమేషన్ దే హ్యావ్ టేకెన్ ఈస్ దే ఆర్ సింప్లీ నెగ్లెక్టింగ్ దిస్ వన్ and they are calculating the gradient at the next point x equal to Vt, that's equal to x plus gamma into Vt minus 1 minus eta into dou g by dou m. But as this is not available, so they are approximated as x equal to x plus gamma into Vt minus 1. This is the next position. Actual position కావాలంటే we require a gradient. మళ్ళీ gradient కావాలంటే ఆ పాయింట్ కావాలి కదా, అందుకని they are approximated like this, right? So we have to calculate the gradient here at the next point, right? So what I will do the algorithm, then you can easily understand. Only thing is, in momentum optimizer we are finding the velocity vector which helps to update the decision variable, and that velocity vector is depending upon the previous gradient and also current gradient. That is in case of the momentum. But whereas in the natural accelerated gradient, what they suggested is, instead of taking the gradient in the current iteration, I suggest that you have to estimate the gradient in the next iteration. You have to take the estimated gradient in the next iteration. You have to take the gradient in the estimated point in the next iteration. So estimated point in the next iteration ఎట్లా వస్తుంది, x equal to x plus gamma into Vt minus 1 and gradient. That gradient will not be available, so simply neglect it, right? So I will do the algorithm, then you can easily understand. So the natural accelerated gradient. So in the step 1, so read the data, eta, epochs, m, c, vm, vc, number of samples. You have to initialize all those things, right? Now step 2, that is, you have to set the iteration equal to 1. You have to step 3, that's equal to sample equal to 1. That sample equal to 1. So these are same, it will not change, right? Now step 3 over. Step 4. So in the step 4 what you have to do is, you have to calculate the gradient. So that's equal to gm. So we are taking the sample by sample, right? So you have to calculate the gradient. Gm equal to so gm equal to minus y minus m into, give me a small time, maybe some, I will show the PPT. So Nastro, right? So we are moving to the Nastro accelerated gradient. nature of accelerated gradient, right? Yeah, fine. So what we are doing here is, so yeah, fine. So you have to calculate the gradient. So as okay, let's assume we are calculating the gradients here, GM and GC. We have to calculate the gradients here, GM and GC. In step 5, what we have to do? Once you are getting the GM and GC, we have to calculate the velocity. So Vm equal to gamma into Vm minus eta into, here you have to take the gradient in the next iteration, t plus 1. Suppose if you take the iteration 1, t equal to 1, you have to estimate the gradient in the next iteration. You have to estimate the gradient in the next iteration, right? Next. Similarly, Vc equal to gamma into Vc, sorry. So I will explain, Nana, in case you are confused, I will explain chestanu. So Vc equal to gamma into Vc of t minus 1 is a t minus 1. It is a t, and you have to find the velocity of the modular parameter at the current iteration based on the gradient at the next point, in the next iteration point. So gamma into Vc t minus 1 minus eta into Gc into t plus 1. That is the gradient of a loss function with respect to the modular parameter at the estimated point in the next iteration. And it is also error function, a gradient of error function with respect to the modular parameter C in the next iteration, at the point in the next iteration. We don't know what is the value, we have to estimate it. So how we get this expression, I will explain. Okay? Fine. Let's assume you are calculated VMT and VCT. Then you have to, step 6 is, in step 6 you are updating your modular parameter, right? You are updating the modular parameter. That's a M equal to M plus Vm in the current iteration, C equal to C plus Vc in the current iteration. That's equal to M plus, what is the VMT? Gamma into Vmt minus 1 minus eta into Gmt plus 1. That's equal to C plus gamma into Vmt minus 1 minus eta into Gmt plus 1. Right? So now these are new M and C values, estimated M and C values. కానీ ఈ M C value కావాలంటే మీకు ఏం కావాలి? You have to find the gradient at this point. అది ఇక్కడ మనకు తెలియదు కదమ్మా, ఇక్కడ మనకు తెలియదు కదా నెక్స్ట్ ఎస్టిమేటెడ్ గ్రేడియంట్ ఎంత ఉంటుంది అనేది. సో అందుకని ఏం చేసామంటే జస్ట్ వీఆర్ అప్రాక్సిమేటింగ్ దిస్ ఓన్లీ, వీఆర్ అప్రాక్సిమేటింగ్ updated M equal to M plus gamma into Vt minus 1 and C equal to C plus gamma into Vt minus 1. Now based on these two values you have to calculate the gradient. ఇంతకుముందు మనం ఇక్కడ ఏం తీసుకున్నాం గుర్తుందా? Here we are taking Yia minus M into Xia minus C into Xia అని తీసుకున్నాం కదా. But here what you have to consider is there is a slight modification in the gradient calculation, that is minus Yia minus, ఇక్కడ ఏమొస్తుందమ్మా M కదా, M రావాలి కదా, M is modular parameter. So we are not using for calculating the gradient, we are consider the next estimated point for your modular parameter. So that's why we are taking the minus M plus gamma into Vmt minus 1, right? And minus here also C plus gamma into Vmt minus 1 into Xia. Here also Xia must be there. So instead of M, I am taking the next estimated point. This one I am taking here. Estimated point, మన కంప్లీట్గా ఎస్టిమేటెడ్ వాల్యూ కావాలంటే మనకి గ్రేడియంట్ కూడా కావాలి, బట్ ఆ గ్రేడియంట్ క్యాలిక్యులేట్ చేయడం మనకు కష్టం. అందుకని వీఆర్ అప్రాక్సిమేటింగ్ ఇట్. సో M approximately equal to M plus gamma into Vt minus 1, that is we are using here. So similarly we can calculate GCT minus 1 as GCT plus 1 as minus YIA minus M gamma VMT minus 1 XIA minus C plus gamma into VMT minus 1. That's it. That's it. Okay. So this is the only change we are considered in case of Nastrov accelerated gradient. Instead of taking the current model parameters M and C, current model parameter M and C, we are calculating the gradient at estimated points M plus gamma Vt minus 1 and C plus gamma Vc minus 1. Vc minus 1. Gamma Vc minus 1. Hope you understand, right? So what we are doing here is we are calculating the gradient not at the current iteration. You are calculating the gradient not at the current iteration. We are calculating the gradient at the next point, estimated next point. అంటే నెక్స్ట్ ఇటరేషన్లో మన పాయింట్ ఇక్కడ ఉంటుందని దగ్గర ఎస్టిమేట్ చేసుకొని ఆ పాయింట్ దగ్గర గ్రేడియంట్ మనం క్యాలిక్యులేట్ చేసుకున్నాం ఇక్కడ. వీఆర్ క్యాలిక్యులేట్ ద గ్రేడియంట్ హియర్ నాట్ at the current point. That's only the difference when compared to the momentum. Remaining all are same. Now you have to take the GMT plus 1 and GCT plus 1 here. Okay, and now once this is, now VMT is available, now M equal to M plus VMT, that's equal to M plus gamma into VMT minus 1 minus this one. While updating you have to consider this, but while calculating the gradient we have to estimated point we have to take. ఎందుకంటే మనకి ఎగ్జాక్ట్ వాల్యూ కావాలంటే గ్రేడియంట్ క్యాలిక్యులేట్ చేయాలి కదమ్మా. సో గ్రేడియంట్ మనకు తెలియదు, అది ఇక్కడే క్యాలిక్యులేట్ చేయాలి. కానీ ఇది క్యాలిక్యులేట్ చేయాలంటే వీ హ్యావ్ టు ఎస్టిమేట్ ద నెక్స్ట్ పొజిషన్. సో దట్స్ వీఆర్ యూజింగ్ హియర్. ఓకే. సో Nastrov accelerated gradient what we are doing is we are updating our model parameter based on gradient at the current iteration, gradient at the previous iteration and also gradient at the next iteration, not at the current iteration. Similar to the like momentum, we are not taking the gradient at the current iteration, but we are considering the gradient, we are estimating the gradient in the next iteration. సో నెక్స్ట్ ఇటరేషన్లో మన పాయింట్ సెర్చ్ స్పేస్లో ఇక్కడ ఉంటుందని అప్రాక్సిమేట్గా ఎస్టిమేట్ చేసి అక్కడ ఎంత గ్రేడియంట్ ఉంటుందో క్యాలిక్యులేట్ చేసుకొని ఆ గ్రేడియంట్ బేస్ చేసుకుని మన పాయింట్ని అప్డేట్ చేస్తాం in case of the Nastrov accelerated gradient. That is the only the change in case of the Nastrov accelerated gradient. Right. So now we will do the numerical calculations for the Nastrov accelerated gradient. I will do it very slowly. So x, y, xia, yia. So it is a 0.2, 3.4 and 0.4, 3.8. Okay. Now step 1, we know we have to initialize all the parameters, like read the data, eta equal to 0.1, gamma equal to 0.9, m equal to 1, c equal to minus 1, epoch equal to 1, ns equal to 2, number of samples, and vm equal to vc equal to 0. Anything left? I think all are covered. Again, step 2, we have to initialize your iteration count. Step 3, you have to initialize your sample number. Right? Now, in step 4, what you have to do? You have to calculate the gradient. Right? So how we calculate the gradient? Gm equal to minus చెప్పగలరా ఎవరైనా minus yia, that is the 3.4 minus, this is the difficult task, what it will be here. ఇక్కడ ఏముంటుంది ఎప్పుడైనా ఎక్స్పెక్ట్ చేయగలరమ్మా? వాట్ విల్ బి హియర్ గుర్తుందా? ఇక్కడ ఏమొస్తుందో గుర్తుందా? ఇక్కడ టర్మ్ ఇంటూ xia, రైట్? xia అంటే 0.2 ఇక్కడ minus c. We are calculating the gradient based on the point in the next iteration, estimated point in the next iteration, and here multiplied by 0.2. I think you agree with this expression, with this expression, with this expression. This is y x, that's it. But what about the value will be here? ikkade untadi evaraina cheppagalaru? Anyone can tell what will be here? Try to, whether it is right or wrong, just try to tell me what is the value. So మీకు ఏం చెప్పాను, we are updating the variable based on the gradient in the next iteration, estimated gradient in the next iteration. So next iteration లో gradient estimate చేయాలి అనుకుంటే you have to take the estimated point in the next iteration. సో ఆ ఎస్టిమేటెడ్ మోడల్ పారామీటర్ వాల్యూ మనం ఇక్కడ ఇంక్లూడ్ చేయాలి, నాట్ డైరెక్ట్ m. So what will be here? What will be here? What will be here? కొంచెం ఆలోచించి చెప్పండి ఏమొస్తుందో. Estimated m and c values for the next iteration that have to included here and here in order to calculate the gradient for the next point, next iteration point. ఏమేమి వస్తుంది చెప్పగలరు ఎవరైనా? అయ్యో బాబోయ్, శ్వేతమ్మా సారీ, మై వాయిస్ ఇస్ ఆడిబుల్ నౌ.
Yes, sir.
ఏమైంది తెలుసా, నేను కంటిన్యూస్గా చెప్తూనే ఉన్నాను, నెట్ ఎప్పుడు డిస్కనెక్ట్ అయిందో కూడా తెలియదు. క్వశ్చన్ అడిగాను మీకు ఈ వాల్యూ ఏమొస్తుందని, ఎవరు రిప్లై ఇవ్వట్లే. అరే ఏమైంది, ఎవరు రిప్లై ఇవ్వట్లేదు, చూస్తే నెట్ డిస్కనెక్ట్ అయిపోయింది. సో ఎప్పటివరకు ఎప్పుడు డిస్కనెక్ట్ అయింది, ఏ టైంలో ఐడియా ఉంది ఎంతవరకు? ఆల్గరిథం న్యూమరికల్ క్యాలిక్యులేషన్స్ వరకు ఉందా?
లేదు సార్, స్టెప్
స్టెప్ 4 ఏనమ్మా?
4 లో అప్డేషన్స్ చెప్తున్నారు సార్.
సో దిస్ న్యూమరికల్ క్యాలిక్యులేషన్ స్టార్ట్ అయినప్పుడు ఉందా?
లేదు సార్, లేదు సార్.
ఓ యూ బాబోయ్. ఫైన్, ఐ విల్ షో బోర్డ్ ప్రీవియస్.
or we will continue tomorrow, sir?
Then better. Okay, it's okay for you. Tomorrow we will continue. But మీకు ఓకేనా అందరికి ఫైన్? ఇజ్ ఇట్ ఫైన్ ఫర్ టుమారో?
Yes, sir. Yes, sir.
But my request is, actually I want to take one more session tomorrow from 11 to 12:30. Is it possible to all of you? Because
Okay, sir.
ఎందుకంటే నా దగ్గర వాకం బోర్డు రేపు ఒక్కరోజే ఉంటుంది. ఈ వాకం బోర్డు లేకపోతే మనం వైట్ బోర్డు మీద డెరివేషన్స్ చేయలేము. సో మ్యాథమెటికల్ క్యాలిక్యులేషన్స్ అని ఐ వాంట్ టు కంప్లీట్ టుమారో ఇట్ సెల్ఫ్. సో డే ఆఫ్టర్ టుమారో మనం ల్యాబ్ చేయొచ్చని. ఓకే. సో
Okay, sir.
I want to take the class tomorrow from 11 to 1. So tomorrow we will discuss, we will start from where we stopped, and also we discuss tomorrow adaptive optimization techniques. So tomorrow we will discuss Nastro accelerated gradient and also adaptive gradient descent optimization techniques. Tomorrow we will discuss. So total 4 optimizers we are going to discuss tomorrow. In the morning session 11 to 1 we discuss 2 optimizers, and evening 7 to 9 2 optimizers. Okay. So for tomorrow మనం ఈ ఆప్టిమైజేషన్ మ్యాథమెటికల్ న్యూమరికల్ క్యాలిక్యులేషన్ కంప్లీట్ చేసేద్దాము. సో మండే మనం ల్యాబ్ చేద్దాం అన్నిటి. ఆల్ ల్యాబ్స్ విల్ బి డన్ ఆన్ మండే డైరెక్ట్లీ. సో మనకు అప్పుడు వాకం బోర్డు అవసరం ఉండదు. ఓకేనమ్మా? నేను గూగుల్ మీట్ షెడ్యూల్ చేసి పంపిస్తాను మీకు రేపు 11 o'clockకి. ఓకేనా?
Okay, sir.
Yeah,
Okay,
fine.
sir.
Thank you all. So we will meet tomorrow at 11 a.m. Thank you. Bye. One. segment 2.
నాన్నకి బౌల్ ఇచ్చి చెల్లి నువ్వు నోరు ముయ్యవరా అమ్మ సారీ నీ పాలెత్తనావురా
టేబుల్ పట్టుకుని ఏం పడవలేదా
ఎక్కడికి ముట్టేస్తారు వెంట్రుకలుగా అయిపోతారు నువ్వు సెట్ ఇచ్చి వెళ్ళి వెళ్ళు సెట్ ఇచ్చి అందుకే ఆగమంటాను ఆ స్పూన్ ఇట్టుకెళ్ళి గ్లాసులు వేసుకోమను ఇంకా ఇట్లే కూర కప్పులు లేదని వేసుకోమను ఇప్పుడు ఏంటి వేసి అక్కడ గ్లాస్ వేసుకోమని చెప్పాను కదా అక్కిచ్చి నీకు పాలు ఇస్తారా నీకు ఇవ్వడం పాలు దరిద్రం ఉంటుంది చెప్పలేను నువ్వు ఎందుకు అలా పిచ్చెక్కిపోతా నువ్వు తిన్నగా ఉండలేవా నోరు మొయ్యి ఎక్కడ తాగిందా చల్లగానే ఉన్నాయి తాగు తాగి సింప్లేస్ మేము కొనుక్కో నువ్వెందుకు అలా ఫ్యాన్కి లాగుతున్నా చెప్పవా ముడికలే నోరు మూసుకుని పో
ఏమమ్మా